We're now recording. Hi everybody, welcome back. Today it is my great pleasure to introduce you Tian, who is from the Chinese Academy of Sciences, and he's going to tell us about the nonlinear evolution of unstable charged de Sitter black holes with hyperboloidal formalism. Tian, the floor is yours.
Okay, so shall we start?
Yeah, feel free anytime.
Yeah, take it away.
Okay. So thank you very much, and I'm very happy to have this chance to report our recent work about hyperboloid formalism, and I also very happy to get suggestions or even criticisms from you guys. So if you have any questions or comments, just interrupt me at any time. So the main topic of this talk is about nonlinear evolution of unstable charged de Sitter black holes, and the outline is the following. So
like this, we saw that this guy that a vector or a covector corresponds to this spinor, right? But actually,
Sorry, Christian,
I need to
can you
say
mute
something.
yourself?
So,
Sorry, 1 second.
okay. Okay. Yeah. Can I continue?
Yeah. Go on.
Okay. First of all, a very brief introduction about the hyperboloidal formalism and the instability of iron de Sitter black holes. And then the main problem of this topic is divided into two parts. The first part is the static solutions and cosmological modes of de Sitter black holes. And the second part is the nonlinear evolution of unstable charged de Sitter black holes. And then finally, the summary and outlook. A very brief introduction, because I think most of you guys here are quite familiar with hyperboloidal formalism. So I think I just give a very short introduction about this point. As you know, for asymptotically flat spacetimes, traditional 3+1 foliation does not cover the future null infinity square plus, but some quantities, in particular those related to gravitational waves or decay rates of the late time tail of black hole perturbations, should be calculated at square plus. So one needs to put an artificial boundary and the corresponding boundary conditions at a large distance and approximately extract those quantities there. So that's the problem. And the hyperboloidal formulation is just a special kind of 3+1. So it solves the above problems by covering square plus with the properly designed time slicing, as shown in this paper. Maybe the simplest example is the hyperboloidal coordinates for the Schwarzschild spacetime. So as is well known, the original Schwarzschild coordinates is of this form. And if we take some coordinate transformation, it can be written in this form, the so-called ingoing Eddington-Finkelstein coordinates. But notice that this form of the EF coordinates is not null foliation. It's just a 3+1 in a Kerr form. As you can see from this Penrose diagram, so this the time slicing of this ingoing EF coordinates is just shown as these gray curves. So it's horizon penetrating, but all of the curves go to the spatial infinity I0, so it cannot cover the square plus. And the hyperboloid coordinates can be obtained by taking this transformation, the so-called height function technique. So here the small h is the height function, and in the radial direction, the r coordinate is compactified to new coordinate z. So it's just the inverse of r. And L here is an appropriate length scale, which will be determined later. And I just skip the details of the transformation and just to show you the result. So the resultant hyperboloid coordinates is of this form. Maybe this form is a little bit different from what you are familiar with, but it's a hyperboloid, as you can see from this Penrose diagram. So eventually, the time slicing of this hyperboloid coordinate is just like this, the red curves. So it's horizon penetrating as well as square plus intersecting. Here, so the h, the so-called shift function, but not quite the shift function because there is a conformal factor here. So it's a shift function in the conformal sense. And it can be easily shown that h squared is just related to this f. And because at infinity, z equal to 0, and at the horizon, f equal to 0. So at both boundaries, h squared is equal to 0, equal to 1. But in order that this coordinate be hyperboloidal, this h function itself should be plus 1 at the infinity z equal to 0 and minus 1 at the horizon. In this case, this square root requires that h squared should have 0 at some point z equal to z0 and be positive elsewhere. So this condition uniquely determines this L as this value. And so in this case, as you can see, in this plot, h squared is just like this. It has a double 0 here. And h itself looks like this curve. So it's a smooth real function. Now in this case, you can draw these curves on the Penrose diagram, and then you can see that it's really hyperboloidal. Okay, so any questions here? Maybe no. So let's go on. In the asymptotically flat case, because our focus in this talk is on the black hole dynamics, and in the asymptotically flat case, hyperboloidal slices have been successfully applied to black hole dynamics. Actually, there are already many papers about this area, but here I just list 2 papers, for example. But how about black hole dynamics in the asymptotically the theta case with the hyperboloidal formalism, where traditional methods doesn't even work? So that's the problem that we are really interested in. But we need to find an interesting problem to use the hyperboloidal formalism. One of these problems is the following. In certain parameter range, the theta black hole under charged scalar perturbation is linearly unstable, as shown in these papers. But how will it evolve, and what is the final state of this instability? So that's the question we will answer in this talk. Actually, the final state of this instability is not quite an open problem, because in this paper, they proved no charge scalar Hare theorem for static de Sitter black holes. So the final state of this instability cannot be a hairy black hole. So one can reasonably guess that the final state will be another de Sitter black hole. Just its parameter will be in the stable range. So, but anyway, it's an interesting problem to see how it evolves, and that is a very good test ground for this hyperboloidal formalism. Okay, so let's move on to the first part of the main problem. That's the static solutions and the cosmological modes of the black holes. Let's recall that for the static black holes, we just use this ansatz for the hyperboloidal coordinates. So for the Schwarzschild case, this h square is of this form, and it turns out that you can similarly obtain the hyperboloidal coordinates for the r and theta black hole. And in this case, h square is shown to have this form, it's closed form, which is also very simple. And here m0 and the q0 are total mass and the charge of the black hole, respectively. And lambda here is the cosmological constant, which is positive in the theta case. And remember that h should be a continuous real function of z, decreasing monotonically from 1 to -1 in the range zc to zh here. So zc is the cosmological horizon, and zh is the outer horizon of the r and the theta black hole. And this function h has a 0 at some point, z equal to z0. And this is the Penrose diagram demonstrating the hyperboloidal slice of the theta r and the theta spacetime. So it's horizon, outer horizon penetrating, as well as cosmological horizon penetrating. Okay, and on top of this solution, we can do linear perturbations and analyze the stability, linear stability of this black hole. So that's the computation of cosmological mode on top of the background. Actually, this cosmological mode has been studied and has been obtained in previous works by other authors. So we need to reproduce their result in the hyperboloidal coordinates. And there are already many traditional methods for computing cosmological modes. It's too many to list here. But in the hyperboloidal coordinates, linear perturbations and cosmological modes has also been studied in this paper through the height function technique. But our choice for computing the cosmological modes is different. So we use a so-called linearized evolution scheme. This scheme is this scheme has the advantage that it can deal with the nonlinear dynamics and cosmological modes in a unified framework, which means that as long as you can do nonlinear dynamics, you can linearize your evolution to compute the cosmological modes with this scheme. So it's quite convenient for us. And this kind of scheme has been used in previous papers like these papers. Okay. So because the details of the computation need to linearize the nonlinear dynamics. So I just skip the details here and just show you some key points and the basic process for the computing. And then the details may be presented later after the nonlinear dynamics if we have time. And the basic process and the key points is the following. The first step is that we should fix the gauge, but it's not a problem in our scheme because in the nonlinear dynamic evolution, we already need to fix gauge. So in the linear case, we just fix gauge in the same way as in the nonlinear case. So this is the first step. And the second step is to linearize the equations of motion on top of analytical numerical backgrounds in our case, it's just the static arm black hole. And the dynamics of linear perturbations is governed by this linearized equation of motion. And if the background has symmetries, the problem can be greatly simplified because separation of variables is possible. And it's also the case here. And then the linearized dynamics is either evolved in real time, and then you can use the so-called Prony method to extract the cosmological modes, or it can be reformulated as a generalized eigenvalue problem, this form, for the cosmological mode frequency omega. So here, A and B are differential operators depending on the background, and P here just appears in this in this perturbation fields. So it's just so data psi is the collection of all the perturbation fields, and it can be written as this cosmological frequency, cosmological mode form. Okay, so we can solve this generalized eigenvalue problem numerically to obtain the cosmological frequencies omega. And so here I just show you some main result of this linear analysis. So as you can see in this plot, so here the horizontal axis is just the mass parameter of the scalar field mu, which is made dimensionless by multiplying m0. And the vertical axis is a very important parameter, q times small q times q0, and this small q is just the charge parameter of the scalar field. And if this parameter is in between this range, lambda min to lambda max, linear instability will occur. So actually, in this plot, the unstable region is just enclosed by these curves. So if you fix cosmological constant lambda, for example, if lambda times m0 squared is 5 times 10 to the minus 3, so it's this blue line, it's blue curve. So the area enclosed in this blue curve is just the unstable region in this case. Okay, so if the scalar field is massless, which means you just look at this leftmost line here, then unstable modes appear for arbitrarily small lambda, the cosmological constant. But if the scalar field is massive, maybe you can draw a line here, then it intersects this blue curve at 2 points, and which is just lambda min and lambda max respectively. Okay, so that's the linear analysis results. And so let's move on to the second part, nonlinear evolution. In order to do nonlinear evolution, we need proper ansatz or proper gauge. So in our case, because it's spherically symmetric, we can have some simple gauge choice. So one of the simplest choice, I think, is just this form. So in addition to the conformal shift function h, which should be dynamic in this case, the conformal factor itself is lifted to another dynamic field chi. So in this case, chi and h are both functions of t and z. And it turns out that this ansatz works very well Actually, we firstly use these ansatz to deal with some problems in a asymptotic flat case, and it turns out it's typically more efficient and more accurate than traditional methods, in particular in long-time evolution. Okay, so I need to present the Lagrangian of the system. So the system we are considering is just a very simple system of the charge scalar field and the Maxwell field minimally coupled to the Einstein gravity. And as I said, mu is the mass parameter. It can be 0 or be non-zero. And to simplify the equation of motion, we introduced the following auxiliary variables. So first of all, because the background is spherically symmetric, so only two components are allowed for the Maxwell field. That's AT and AZ. And we take the so-called radial gauge, which means that AZ is vanishing everywhere. And we denote AT as A and introduce the auxiliary variable B for this gauge field. And for the scalar field, we just introduce this zeta, which is roughly the time derivative of psi. And so here, over dot means time derivative, and prime means z derivative. And the equation of motion in our ansatz here turns out to be very simple. And we divide the equation of motion into two classes. The first class is a system of evolution equations with a very simple structure. So these 5 equations. And the last 2 equations are just for the scalar field. So this pair just forms a standard wave equation for the scalar field psi. While these first 3 equations are all advection equations, and the first 2 are for the gravitational field, and the third one is for the Maxwell field. And the second class are 2 constraints. So the first one and the second one, so there are 2 constrained equations. And these 2 equations are preserved by the evolution equations, which means that if your initial data is initial data satisfy these 2 constraints, it will satisfy these constraints will be satisfied forever, theoretically. But you can use these to check the numerical errors. And let me emphasize again that no artificial boundary condition is needed at the event horizon or the cosmological horizon. Okay, so let me give you more details about the numerical implementation. So we have 5 fields here. So whose time evolution can be calculated through the 5 evolution equations. And numerically, the t direction is we use the explicit 4th, 5th order Roncourt marching with adaptive steps. And for the z direction, we just use Chebyshev pseudo-spectral expansion. Because there are 2 constraints and 5 fields, so we have the freedom to choose the initial data of 3 dynamical variables. And in practice, we just use this very simple Gaussian form for the scalar field, and also these 2 forms just for simplicity. And the result of the evolution is the following. So the characteristic behavior of the scalar field can be shown in these 2 plots. On the left, it's the value of the absolute value of the scalar field on the apparent horizon, and the plot on the right shows the energy of the scalar field. And as you can see, there are basically two stages during the evolution. At the first stage, the scalar field is exponentially growing, and in the second stage, it exponentially decays. Except that if the scalar field is massless, then it's not exponentially decayed, just saturated to a constant. But because it's massless and it's how to say that, because it's massless and if it's a constant, then actually the configuration is trivial, right? Okay. So this is the behavior of the scalar field. And another important aspect is the charge, the evolution of the charge of the black hole. So as you can see from this plot, if the scalar field is massless, then at the second stage, the charge of the black hole decays exponentially. In this case, the final state should be Schwarzschild black hole, the Schwarzschild, the theta black hole. And if it's massive, then the charge will decrease to settle down at some constant value, some finite value. So in this case, the black hole becomes a less charged black hole. But anyway, during the evolution, the theta black hole is discharged. Importantly, the final state is about the black hole because, as I said, the final state has no scalar field or a constant scalar field if the scalar field is massless. So that's also about the black hole. Okay. So the numerical errors and the convergence are shown here. So you can see that it works very well because the numerical errors are always very small, and the spectral convergence is very good. So let me give some more details of the cosmological computation, because now we have the nonlinear dynamic equation that we can do linearization. For the Arndt theta background, gravitational and electromagnetic perturbations are decoupled from scalar perturbations, and so they can be consistently turned off. So we can only consider the scalar perturbations independently, and the dynamics of the scalar perturbations is governed by the linearization of the corresponding equation of motion, these two equations of motion of the scalar field. And in the linear evolution scheme, no boundary condition is needed for hyperboloidal coordinates, as I said before. And the time translation symmetry of the background enables the following form of expansion. Actually, it's just the standard form of the cosmological modes. Here, delta psi and delta zeta are perturbation fields of the scalar field. Because of this form, if you plug the perturbation fields into the linearized equations motion, you can see that the time derivative in the linearized equation motion can be just replaced by this number minus I omega. So in this case, we can get the following linearized equations of motion. Here the operators A and B have this form respectively. Actually A is differential operators because you can see the Z derivative here, and here. So anyway, this is a generalized eigenvalue problem for omega, and numerically, you just do discretization in the z direction. In our case, we do the pseudo-spectral expansion in the z direction. So eventually, this z derivative just becomes a matrix, and then this eigenvalue, generalized eigenvalue problem for omega just becomes generalized eigenvalues of matrices, and you can easily solve them numerically. Okay, so that's the main problem, and now we can give some summary and outlook. So first of all, the hyperboloidal formalism has the advantage of no need to put artificial boundary conditions when dealing with symptotically flat or de Sitter black holes. And in our problem, the nonlinear evolution of unstable charged de Sitter black holes can be performed with high efficiency and long-term accuracy in a very simple form of hyperboloidal coordinates. But if we want to generalize our very simple form of simple nonlinear form of gravitational dynamics in the hyperboloidal coordinates to less symmetric cases, it turns out to be not so easy, and we are still trying to succeed. And on the other hand, further exploration of optimized or adapted formalisms of numerical relativity for various problems is still interesting and important. So I think I just stop here, and thank you very much.
Thank you for your beautiful talk. That was really great. I'm going to stop the recording here, and then we can all ask you lots of questions that I'm sure we have.